Okay, it's almost noon, so I bet you're getting hungry. I'll try to make this entertaining. All right, I want to talk about how graphs can become just another big data primitive today. But we can't go into that until we talk about why graphs are cool. So what better way than a demo? Here's some work we're doing with Mount Sinai Medical School, Joel Dudley's bioinformatics group there. And it's a really good illustration of what we can do with graph, both visually and in terms of analytics. So molecules are just small graphs, and their properties, basically the vertices are different compounds from the periodic table, and the way they relate three-dimensionally is really important structurally. And so we can look at, in particular, the similarity between different molecules and compounds to determine their chemical activity and how they could be used therapeutically. And so what we've done here is we're going to take all the known therapeutic compounds and compare them for their similarity graphically. We can use all kinds of similarity measures, and we can even display the similarity measures can be done using graph analytics, looking for similar subgraph patterns, as well as looking at the visualization that displays the similarity. For example, if we have a set of links that represent how similar different compounds are to each other. For example, here, I have a compound called, oh yes, I got one I can't even pronounce. Well, dimethyl prostaglandin. And it's got a similarity score with all these other compounds you can see here, starting with really high similarity of 0.877, it goes up to 1. And then if we look in this graph over here to the right, we actually see these top-ranked ones clustered around the compound itself, which is in light green down there at the bottom. And those edges are the similarity strength measures, so they're getting pulled just by the physics of the layout near each other. So it's an interesting problem, and it can become a large-scale problem if we do this for all compounds, because it's really a O to the n squared problem, where n is the number of compounds studied, and we're talking about millions of compounds. In this case, we're just doing it for 1,300 compounds. I can hit another one. It's just kind of fun to do. Let's look at another compound. So you can see the ones that are similar coming together there. So yeah, graphs are cool. But they should be just another big data primitive. So how did they become just another useful big data primitive? Anybody? They haven't. The problem is that, we were part of the problem. So we set off in the right direction. We realized, this is a slide that I did at the first Graph Lab conference, that the big data wizards and the open source community and the pioneers had been racing along at warp 9.9 with graph analytics, leaving behind the potential beneficiaries, the larger community, the ecosystem. In fact, those beneficiaries at large scale were only grokking Hadoop. They weren't ready to talk about graph analytics. So we said, okay, let's go reduce the tooling drag for graph analytics. Maybe there'll be some uptake. And we started working with, I started working with Carlos Gestrin, who's founded Graph Lab, to construct a large-scale graph processing pipeline in. How do we build graphical models? How do we train them? How do we serve them? And so on, and get insight and prediction out of them. And so that was all great, except Intel had been working in big data before that, and the interest in the work in the open source community through our enabling work and in our software efforts, we had seen large, hockey stick uptake in the interest in big data analytics. But then when we started talking about this graph processing, the interest dropped a little bit, and then we said, okay, well, why don't we go a little bit deeper on graph and get a little more interesting? We can do all this subgraph pattern matching and belief propagation, all these things, and the interest even dropped off more. And the spaceship started going beyond warp 10, and it was falling apart, and we said, okay, wait, there's something wrong. We're leaving something out. Don't ignore what's popular. If you're going to do graph analytics, you got to bring it into relationship with all the big data tooling that's out there. You've got to put it under the UIs that people are used to relating to, the languages they use, SQL, Python, R, whatever it is you use for data science, MATLAB. Let's put it in there. It's just another tool in the toolbox. And so, in fact, in big data in particular, these aren't really data primitives. That would be things like integers and so on. But these are data structure primitives. And they're really useful, and graph is just one of these. You might use key values. They're a great dictionary technique, and you might relate to them using some very popular tools and languages that are shown at the bottom. Same with documents, great for describing hierarchical structured information, and clearly in a lot of popular formats that are consumed by systems, XML and JSON. You've got columnar stores going crazy right now, where you have a key, column value, and it's great if you want to do something to everything in a column, transform it, filter it. Of course, you've got the old school relational database organization, and then you've got graph, and you've got matrices, and you've got a ton of other representations. And they're all good, and they're all part of data science. And the systems are getting better at exposing these primitives through APIs and libraries and doing it in different ways. There's graph again. To understand how we can bring graph into relation with everything else, we have to figure out how those primitives are used in practice. Well, all right, I won't bore you to death with this. We've all seen these pipelines. This is a typical data science pipeline. It's the kind of thing we do all the time, and I'm sure you do too. You have to do the data preparation, and then once you get the data to a certain state of preparation and you've done a data quality report, you can do your feature engineering, you can build your structured models and train them and validate them and then serve them to other services or to the user for insight. Now, here's a question for you. Here's something we could build a data representation for. It's a personal learning knowledge graph that we're working on with Intel Education Group. And in it, you can see that we've got a person that's taking classes of different subject types on the left, and a task level, or basically the grade in school or higher education they're in, the type of specific learning task they're working on, and the outcome, like how well, that dreaded midterm or final that you're taking. And then if we have a learning plan, at the bottom you see a learning plan and a learning goal, and these are related imperatives, and they come together with the learner at the proficiency to give us an evaluation. Is this person doing above average or below, and how can we recommend that they learn more effectively using all of this information? If you were trying to solve a data science problem with a personal learning knowledge graph like that, how would you represent it in a system? How would you think about it for doing the feature engineering, the model training, the scoring, and all of that? How? I mean, the problem is that you can interpret this information in multiple ways, and you want to do that throughout the problem cycle. It's not just a graph. It's not just a relational problem. It's not just a columnar problem. And so in reality, what you end up doing, even when you're doing graph analytics, is you go back and forth between different data structure paradigms, and you work the analytics across that through the pipeline. You may start by engineering features in the form of thinking of them in terms of data frames or tables, computing averages and ratios. You may even take inputs from other models that have done segmentation and clustering. You may then transfer that over to and build a graph out of it and create a graphical model that you're going to run a graph-based classifier on. Maybe you're using loopy belief propagation to do some kind of binary classification on some priors. And then you may pull those results back into the frame to actually do your model performance statistics, because that's not very convenient to do in terms of graph analytics. You want to do it, think of it more as like coming in from above on the graph and doing summarization, right? You don't need to traverse edges to do that. So that in reality is, you can see how these data structure primitives would interplay in a problem like that. So the learning is that the primitives are not used in isolation, and that's why, I mean, that's part of the problem with doing specialized graph systems and building specialized graph pipelines. And so, yep, I'm guilty of that, and it wasn't a successful strategy. And what does that lead to? A big tooling mashup. So if you go, okay, great, I get it, I'm going to go put that together, I'm going to go do it. Well, you'll do this anyway. You'll get dragged to this, whether you like it or not, when trying to solve a problem with graph at the center of maybe the analytics. And you can see that there's a whole slew of things that you're going to have to bring into play, different languages, different tools. I've said this before, and I'm sure you realize it. So the tools are not used in isolation either. We have to figure out how to cope with that. So today I'd like to suggest maybe a couple of directions. And these are things that Intel's working with the academic community on and the open source community on, and partnering with startups to try to solve. Direction one, we can unify these data structure primitives and processing on some kind of workflow-oriented engine. Can you imagine what that might be? Anybody work in big data tooling? How many of you work with big data tools today? You know, distributed parallel processing. Okay, great. There's like half the audience. Seen that before? All right, so Apache Spark is a great direction. You know, for those that don't work with it, the fundamental idea being that there's this way of putting data into a data set and organizing it into collections that can be used with all kinds of abstractions. And so we can do all kinds of entity-based machine learning with the ML lib. We can do graph-based learning with GraphX library, and we also have data streaming services and data preparation services, and we can even do queries on this. And Spark is great because it's like MapReduce 2.0. It allows for in-memory processing because the Berkeley team had figured out how to make resilient distributed data sets in memory that machine crashes and it's quick to recover and we don't lose anything, and also provides for the iterative performance we're looking for algorithms. So this is great. And the beauty is that the community has rallied behind this and is enriching the libraries like crazy. For graph, what it means is that, well, there's GraphX library that I referred to. This API supports a graph processing engine on Spark, and it dips into these RDDs, and it can take several tables and represent a graph that way. And because the graphs are fundamentally collections of tables under the hood, that means we can analyze them using relational methods if we had a query interface above it, and maybe even a transaction interface. So, but we can also do Pragle-style vertex programming on it and do graph analytics quite well. So that's really cool. And it embraces this paradigm of tables to graphs and graphs to tables. But it needs to come along as well. So if we're going to make this direction happen, we have to get better language bindings. And one that my team is particularly interested in is bringing better Python support for graph, better R support for graph. Spark already has some language bindings, but it doesn't have one for GraphX, for working with graph. And so my team is actually bringing that. And this is the way that the Python environment would interact with the Spark cluster. It's quite straightforward. We basically serialize Python functions over into the Spark environment from your Python 2.7 that you've downloaded, and then return results back into your Python context after they're complete on Spark. Transformations, actions, and graph operations. And so it might look like this. What we're working on is you could define a set of vertices, give them vertex IDs and names, give the edge relationships with properties like knows, so two people, Alice and Bob, know each other, build a graph out of that, and then you can add values. You can see that we're doing this lambda function where we're adding a fixed value to all of the elements in that graph, and then we're taking the top two values. So on the left is all the Python. That's the script you would write, but you could do this at any scale on Spark, and it's written in Scala, Java, something similar to Java, and executed this way on RDDs in Spark for you, and you don't have to worry about that. And this is just a small list of the things that we're doing to actually roll that library out. So I would say maybe around the end of the year we'll see it in the Apache GraphX project. And what's cool is you can see some of the analytics that we're bringing there that you'll be able to access at the bottom, including SVD++ and so on. So that's direction one. What would it give us? Well, we get the feature engineering, we get the model training, we get limited language binding, but it's getting better. And it still lacks transactions and model serving, really. I mean, unless you're going to just serve the model directly off the model and not do anything sophisticated with that, the scoring. Or does it? How many of you heard of Velox? Okay, so there's an early UC Berkeley AmpLab project to bring this to the next step. If you don't know, the badass stack, the BDAS stack, that Berkeley stack is the one that was really the impetus for Spark, and this is where Velox is. It's the same people, and basically the idea is to take Spark, use that for batch training of the model, but create a more significant model management framework around that so that we can schedule updates of the model and serve the model over to scoring so we can make predictions on it, bring predictions in, push scores out, and do that at scale. Cache the things we need to cache and keep these things synchronized, all on Spark. And this would make it a more complete solution. All right, so that's direction one. Direction two, we could unify the primitives and processing on a relational database. And you've got to ask the question. The database community is up in arms about the direction that Spark and some of these things are going. They're saying, look, we could do all that in database. Why don't we do that? Well, they're trying really hard to do that. So with respect to graphs, here's many of you might not know about this, but last year a paper was published by the SAP HANA team, this great in-memory distributed database, columnar database, and they were doing experiments to see if they could do performant graph traversal with SAP HANA. And they actually succeeded pretty well with that. See, they were making the same argument I'm talking about here. On the left is a relational database that already serves applications today, and most of the data in the world's out there in relational databases somewhere, right? I mean, that's the argument. On the right, well, there's a bunch of companies standing up these graph databases, Infinigraph, Neo4j, you can go find a whole list. Do we need two databases? Can we bring these things together? So that's the basic question they were trying to answer. How could we eliminate the inefficiency of having to replicate data and then synchronize things and federating queries and things like that, right? So they tackled it for graph traversal. So basically, graph traversal is a problem of scanning a column of vertex sources and looking for the vertex targets that you're after, and then scanning the vertex targets and going back to the source column and doing that over and over. And they found a way to organize the columns into blocks and do efficient two-stage indexing that would allow them to do performant traversal in a nutshell. And they did it on a number of graphs that probably many of you that are working with graphs are familiar with, the Amazon graph, the California roads graph, the patents graph. And they found that the time to do these traversals and against the number of iterations was quite good. The green line is the one that they were experimenting with called Groton. And some graphs trip it up like the Amazon graph, but often it's quite a bit better than just a brute force scan. And I think it's coming along. They continue to do work on this, but they're not really talking about it much right now. But I think it'll surface at some point. You can go beyond that. Obviously, it's not just about graph traversals. You want to look at graph analytics. Can you do all of that inside the relational database? And so here's a project. Intel has an academic collaboration framework called the Intel Science and Technology Centers. The one that's for big data is hosted at MIT. It's a hub and spoke model. We have many schools involved. And so Sam Madden's team there, who's quite good at databases, they've been looking at this problem with us. And so here's a study where they compared the performance of Apache Giraffe, a graph processing framework in the Hadoop ecosystem, with their database. I think they're the guys that did HP's the Vertica database, so they've been using a performant database to study against that, and they found that they could do PageRank and shortest path faster with the database than they could on Giraffe, which isn't the best baseline, but it's getting somewhere. I mean, I would really want to benchmark it again against GraphX and see how that does with the benefits brought there. But it's quite compelling, and in fact, the story gets more compelling if you think about the things you do before and after you run an algorithm like that. If you're going to do projections, selections, and aggregations, other pre and post processing, and you can keep everything in the database, so you don't have to be moving the data around to do the Giraffe-based analysis, and then you're running something, running these things elsewhere, either in a database or on HDFS into MapReduce. You can do a lot better, and you can see that their green bars got a lot shorter in terms of time, which is good. And so relational and graph looks better together. And so this is definitely a direction to continue to push on. You should go try to find Alec Jindal's blogs and take a look at that and watch for more. But I think it really comes down to how you want to impart, it comes down to whether you started in databases or started with data workflow systems, whether you like procedural or declarative languages, or whether you like query languages or scripts and so on. And so, here's a shortest path algorithm that's cast in SQL. Is this the way that you like to program these things? That's a question for you. And there's a lot of other work going on. I just want to point that out. Even if you're not into SQL and you don't think it's going to express everything you need, there are actually people working on new query languages that will be able to, big dog, that'll be able to express a lot more. Think of it as a machine learning query language, and to allow multiple systems below to be expressed through that query language and consumed by applications, viz, and languages above. So, I think this type of narrow waistline approach is we're going to see a lot more of it going forward, and it's going to make the tooling a lot easier to deal with. So to summarize direction number 2, it provides the feature engineering, transactions, model serving. Is it performant model training? We'll see. I mean, the databases have to catch up with what Spark is doing, I think. And at the end of the day, is it just going to be another Spark behind a query language of some sort? It might. These things are blurring, I think. In fact, so who favors starting with the database and trying to do everything in database? All right, who favors the Spark direction? All right, well, this room, clearly Spark's the winner. But like I said, will the lines blur? I mean, I see these things converging. So at the end of the day, I think that Spark adopts transactions. The databases do all the in-database analytics, and it's hard to tell distinguish between the two. So the takeaway is, no matter which way you go, direction 1 or 2, you want to do all the distributed parallel processing in one place. And by the way, the earlier comment about starting with a small subset of your data and working out the problem that way, do that. Don't go to the scale right away. But then work it through one UI. And so the last thing I wanted to talk about is that Intel is trying to help in this space, and we'll do it as long as there's a gap. So we're both doing it through the ISTC that I mentioned and all the interactions with these companies and consortiums and open source community. We also have built a REST API and provided unified UIs above it for the Python library and the query interfaces, so that we can access even Apache Spark and do everything end-to-end on Spark and other tooling. And to fill in some of the lacking data structure primitive support that is clear today, and allow you to do the end-to-end pipeline from data preparation all the way through scoring. And it's available beta. You should talk to Jesse at the table outside if you're interested in getting in the beta trial for this, but it lands right on Spark. And so just to show you what that really looks like, so here's a web link graph. It's IP and domain relationships and reputation. So with Intel Security, we studied the reputation of objects in the web and did a guilt by association study. So this is what they have today for information. And there's a slight change here. You can see that we've been able to score more certainly some of the reputations out there. And we did that through the toolkit in this unified programming environment. So just so you get a sense for what that would actually feel like, how many of you use an IDE like Eclipse or IntelliJ? Okay, perfect. Well, that's why we did it like this. So here you go. Here's a Python script to run completely the data workflow from data preparation all the way through ROC for that web reputation analysis. And so it's all in Python, standard Python. You can go download Python 2.7 and install the Intel Analytics Toolkit Python library, which is a data frame library very similar to Pandas, except it connects with the REST server and allows you to access Spark and the other tooling to do this at scale. All right. So you can see quickly we take all the data sets that we got from Intel Security, we extract the fields, we filter things for errors, we do the reputation mapping, we drop IPs that we don't want, we extract the domain fields, the domain IP domains, we calculate the priors and label everything. We put this all into a publication frame. We do a bunch of joins. Yep, there are the joins, the joining of multiple frames, the publication domain history frames, and we assign a bunch of labels for the priors and samples, and then we build a graph. And so this is what the graph construction looks like. You can see we're adding vertex rules and edge rules, and then graph equals big graph right there. And so you can build a 15 billion node graph using this Python script right here. And then we run LBP, and that's what it looks like. So it's very Pandas-like. You can see right there all the parameters that you can control as a data scientist. And then out we spit some graphs to allow you to assess its performance. So when I run it here, it's actually connected to Hillsboro, Oregon. We have a cluster there. I'm going to cross my fingers. So I'll tell you one thing right away. Oh, thank you. So that's contacting our REST server, and we're expressing all these data science operations through a standard API we built called the Data Science API, and it's a bunch of JSON objects, puts, gets, and then it'll send over the algorithmic commands, check for status, report updates, and so on. And you can see it running right there with some feedback on how things are proceeding. This is all running on Spark, like I said. The one unfortunate thing is big data just isn't that fast yet, right? We can't do much about that. This doesn't change the performance of Spark at all, just the way you use it. It's different than doing like a PySpark binding or a PyGraphics binding in the sense that we actually hide some of the clunkiness of like a direct mapping from you, and we can do things that are more that you'd expect to be able to do with the Pandas library that aren't covered there, some more complex operations, and we can do lazy execution and things like that. So it's pretty cool. If I were to run it, I'm sure it would run to completion, so I won't bore you with that. All right, so I think I'm wrapped. So yeah, we started with a vision. We're going toward that vision. It's taken a ton of pivots, but I think we're still on track. We finally figured out how to relate graph so that graph becomes just another big data primitive. Thank you very much.
Thank you very much, Ted. Our next speaker is from Pandora, Oscar Kelma. He's going to tell us more about what they are doing behind the scenes.